Okay, everyone, please grab your seats. We'd like to start the evening. Okay, let me get started. My name is Martin Meyer. I'm a professor in geophysics here, if you have not seen me or heard me before. And I'm very much delighted to introduce tonight's keynote speaker, Dr. James or Jim Mori from the Disaster Prevention Research Institute in Kyoto University. I don't recall when I met Jim the first time. It must have been quite some years ago at a conference, and we've been, closely interacting or exchanging emails once in a while here and there. And so it's a great, great pleasure for me that Jim is here on the efforts of one of my postdocs, Hugo Cruz Jimenez, and he'll speak about the 2011 Tohoku Earthquake and recent results and findings related to this event. Now, some of you might have attended my lecture on this event shortly after it occurred, and I just spoke about the effects of that earthquake, and tonight we learn more about what actually happened during that earthquake based on new geophysical and seismological findings. Now, Jim Mori is a very interesting character and scientist in the sense that he combines his interest in earthquakes and volcanoes simultaneously. He uses observational data and runs experiments like going out with a ship and collecting new data. And so he's been working both on earthquakes and volcanoes, which is quite uncommon to combine these two interests. Now, Jim got his PhD back in 1984 from Columbia University, and then he went to Papua New Guinea to work on the Rabaul volcanic caldera there, and then he returned to the US to work at the USGS for a number of years until 1998. And then he took up a professor position in Japan, where he's been since 1999. And as I said, he combines this unique interest with working on earthquakes and volcanoes simultaneously. Now, I just realized that it's exactly 30 years that Jim published his first paper. I'm not sure if you remember. It was in 1983 on earthquake dynamics. And that's a topic that we still currently work on. So Jim has been really at the forefront of earthquake seismology research. And I'm very, very glad that he's here tonight to tell the latest findings about the 2011 Tohoku earthquake. And without further ado, I'd like to give the stage over to Jim.
So, thank you, Martin. So today I'm going to talk about the Tohoku earthquake, as Martin mentioned. And I'll spend the first time talking a little bit about the earthquake, and the second about this very large project we've had to try to understand what happened during the earthquake. And the reason there's this photograph of a big ship is that this project was based on a borehole that was drilled into the ocean floor down to the fault of the earthquake to learn about it. And so I'll explain later about how we use this ship and some of the data that we gathered on it. Okay, so this earthquake happened on March 11th, 2011. Unfortunately, many people were killed. There was a very large tsunami. Probably many of you have seen the videos and the photos from it. It was very costly to Japan, about 30 trillion yen, and that's about 1.25 trillion Saudi Arabia riyals. So very costly, a very tragic event for Japan. And it certainly it was the largest earthquake Japan has experienced, and so the many seismologists in Japan are working very hard to understand it, and of course we want to learn from this particular event so that we can help prevent such disasters in the future. So what is this picture? This picture has a lot of little yellow and red circles, and they're locations of aftershocks. And probably most of you know after you get one big earthquake, there's lots of smaller earthquakes that happen afterwards, which we call aftershocks. And if you plot up where all those aftershocks happen, essentially that tells you how big was the fault, how much of the area moved or ruptured during that earthquake. And so this one had a length of about 450 kilometers by 200 kilometers, and it was a magnitude 9. Magnitude 9 is very, very large. Oops, what happened? And for example, it's 1/4 the area of Japan, so it really affected a very large portion. Saudi Arabia is much larger, but still it's about 1/25 the area of Saudi Arabia. So again, it was a huge earthquake. It really affected a very large region. The fault moved over a very large region, and because of that, it certainly did a lot of damage, and we'll talk a little bit about the shaking and the tsunami that happened from this earthquake. The last picture was a map. This is what we call a cross-section. So now this is like taking a slice through the earth. So this is the ocean here. This is the ocean floor. And it happened on this fault, which is slanting downwards into the earth. And so it happened on this wide fault, close to horizontal, but maybe dipping at an angle of maybe about 10 to 20 degrees. And so if you've studied plate tectonics or geology, you know that the earth is made up of these plates that are always moving around. So this is the Pacific plate here, and on top is the continental plate, and the Pacific plate is going down underneath the continent or down underneath the Japanese islands. And we call this process subduction. So this is the subduction zone. This is the subduction zone plate boundary fault where this giant earthquake happened. So it happened right along this very large fault here. Just to give you an idea of how big this earthquake was historically, it was about the 4th largest earthquake that happened since earthquakes have been recorded, so over the last 100 years or so. This picture shows the sizes of earthquakes. So this is the length. So the very largest giant earthquakes like 1960 Chile or the 2004 Sumatra ruptured more than 1,000 kilometers in length. The Tohoku earthquake was not quite as long, but it was a little bit wider, and the area is not so big, but the reason it's a magnitude 9 is because the slip was very large. Actually, the slip was much larger, not much larger, but larger than some of these other earthquakes. And the way seismologists calculate the actual size is we take into account both the area and the amount of slip, and that gives us this magnitude 9.0, and it's about the 4th largest earthquake that we've ever recorded in seismology. So I mentioned about slip, and that's really one of the features of this earthquake. The fault moved a very great distance, and we had some instruments on the ocean floor out here, and so this place here actually moved 24 meters off to the southeast, and this one moved 15 meters. And these are actually the largest displacements that seismologists have ever seen in an earthquake. I think up to now the biggest movements we've seen directly are about maybe 10 meters or a little bit more, 15 meters. But this one really moved a lot, 24 meters. And we actually think the fault even farther out to the east moved maybe 50 or 60 meters. So it's really a huge amount of slip that happened during the earthquake. And actually for a seismologist, it's a little bit difficult to imagine that faults that are rock surfaces can move so far in a single earthquake. Usually when you think of earthquakes, and maybe you haven't felt so many earthquakes in Saudi Arabia, but an earthquake by the name is that the earth shakes or quakes. And so we usually think of the shaking that happens during an earthquake. And usually the big part of the damage, the thing that causes buildings to fall down, or that usually has a lot of problems for people, is the shaking. But this earthquake was a little bit different. It was not the shaking that did the damage. It was a tsunami, and we'll talk a little bit more about exactly what a tsunami was. But in this particular earthquake, actually very few people were killed by collapsing buildings or by landslides or by other things that are due to the earthquake shaking. So the real story of this earthquake is the tsunami, is the wave. And the shaking part was very strong, but it didn't do so much damage in this earthquake. Actually, one reason is probably because Japan has so many earthquakes, the engineering standards are very high. And so even though the shaking was very strong, most of the buildings did okay. So there were some buildings that collapsed, but these were the minority. And most of the buildings did very well, and so that was, if you can find anything good about this earthquake, that was one very encouraging point, that the shaking damage was relatively small. But as I said, it was the tsunami that really was the story of this earthquake. It was the tsunami that came and killed all the people, that destroyed all the buildings. And here's just a photo of the tsunami coming in at one place. Japan has had lots of tsunamis in the past. They've tried to reduce the effect of them by different kinds of structures. One is to build walls, but this particular case, the wall was not high enough. So this is a tsunami coming over about a 12-meter wall here. And so unfortunately, the tsunami was just much bigger than was expected. And so that was part of the problem with this earthquake. Okay, so what's a tsunami? Basically, it's a big wave. Or actually, I should say not a wave, but a wall of water that comes, hits the shore where an earthquake happens. And it's caused because the ocean floor moves during an earthquake. And especially if it moves vertically, it causes this kind of wave. So this picture here shows what's happening before an earthquake. So maybe the 100 years or 1,000 years before an earthquake, this plate is very slowly putting a lot of pressure on this one. So this is the subduction zone that I described earlier on. This is the Pacific plate that's going down this way, and it's pulling this upper plate, or it's sort of locked here, and gradually this plate is being pulled down. And when an earthquake happens, what an earthquake is basically the sudden release or the sudden rebound of this electric energy. And so when an earthquake happened, this part suddenly snaps back. So it's been building up all this stress, or building up all this pressure for maybe 100 years or 1,000 years, and then suddenly it's all released in maybe a few minutes. And when it's released, this ocean floor moves upward. And when it moves upward, it displaces this water, and that's what causes the tsunami, which comes on shore. It also causes shaking, which, as I said, could do damage to buildings. So the size of the tsunami, how big it is determined by how much the floor moves, the seafloor moves. So, if it moves 1 meter, you get maybe a moderate-sized tsunami. If it moves 10 meters, you get a much bigger tsunami. It also depends on how deep the water is, because the deeper the water, the more water is displaced when the seafloor moves. So deformation in the deep water here makes a much bigger tsunami than the ocean floor moving in the shallow part here. And then there's lots of other complicated things like the shape of the ocean floor, the shape of the coast, and all of that controls on how large the tsunami is that comes by. And it was very big. So here's one famous photo that the tsunami is actually coming in over a wall that was built here to sort of protect the city. And you can see these cars that are being washed away and boats that are being washed away. And actually I visited this site, and if you look at this sign here, we went to that sign, whoops. And so this is that same sign, and so this is the wall. And so you can see it's maybe about 3 meters high. and it's on maybe about 1 meter above the normal sea level, so this is probably about 5 meters above the sea level. So the wave here was at least 5 meters high. Actually, it was much, much higher than that. But you can just see how the wave is coming in over that particular wall. Here's another photo, and this shows a much higher. So if you look at this building very closely, you can see on the upper 2 floors, all these panels are still in place. But the bottom 3 floors, all of these are gone and all the windows are broken. So the tsunami came at least this high. And so here the tsunami was probably about 10 meters or 12 meters high. So that again just gives you an idea of how high the water was when it came in on this huge wave. I mentioned there were lots of walls along the coast of Japan that were built to protect places. Unfortunately, lots of them were just not strong enough, and they were destroyed by the big waves that were coming on shore. So all of these things just point to this problem that the tsunami was much bigger than the people in Japan expected. And what that means is that the slip on the fault, or the bottom of the ocean, moved much more than people expected. And so that's really the big problem. That's what we really want to understand in this earthquake, is why did it move so much? Why did the fault move 50 meters and cause this huge tsunami from this event? Just another photo here, you can see the wave actually coming in and destroying these houses that are on along the coast here. Okay, I think the next one is a little bit of video, and you can get an idea of what it actually looks like. And so this was taken in a helicopter, and here's the tsunami wave coming in. And so it was very apparent, and you can just see this line here. And one thing different about a tsunami and sort of regular waves that you see at a beach is it's actually not a wave. It's actually a wall of water. And that's what makes it so strong. Actually, it's going back, and it's not one, but actually there's a series of waves that are coming in. And so I use the word wave, but as I said before, it's not a wave, but it's sort of a step. And that's why it's so strong. If we're just a wave, you know, if you're standing in the ocean, a wave comes, you sort of get hit, but then it goes down, and so it's not so powerful. But a tsunami is very different because it has all the momentum, it has all the force of the water behind it. And so even if it's only 1 meter or so, it's still very strong. And so you can see the wave coming in, and I think pretty soon, okay, here you can see the wave coming in through this small village here. And you can just see the power and how these buildings are destroyed. And this extended over a very large region, maybe over 200 kilometers along the coast was exposed to these very, very powerful waves. And if you have a very strong building, okay, here this is good. You can see the tsunami coming in over this rice field. So here's the tsunami coming in. It looks black because there's sort of a lot of soil. You can see all the cars and debris that's being carried, and it's just washing across the rice fields along the coast here. So some places it moved maybe 2 or 3 kilometers. It moved maybe 5 or 10 kilometers up some of the rivers, and so it was just a huge wall of water. Here you can see it kind of pounding in this little basin here, and all the debris that's being carried behind it. So that's the power. That's what really was the devastating part of this disaster. Here's a survey measuring how high the tsunami was along the coast of Honshu. And maybe it's a little bit hard to see, but this is 10 meters here. So for maybe about 200 kilometers of the coastline, a very long part of the coastline, the tsunami was over 10 meters. And this is 20 meters, 30 meters. The very highest, what we call run-ups, was over 40 meters. But still, there are many places that were 20 or 30 meters. So that's like, 30, 3, 4, 5 stories high. So it's actually I visited these places, and it's very difficult to imagine such a huge wall of water coming in. And this is what really surprised seismologists like me, that we could get such a huge tsunami. We've had many places in Japan that have had tsunamis in the past, but we really were not ready for one of this size. And that was the problem. It was just much bigger than all the preparation that was being done to protect the cities along the coastline. So what do? How do we learn about this earthquake? Well, as a seismologist, we can study all the seismic recordings, the seismic waves. We can study the videos of the tsunami. We can study a lot of the records of how the earth moved. Another way is to actually go and look at the fault. Try to get a sample or try to make some direct measurements on the fault here, and that's what we did. And so that's this project that we call JFAST, was to drill a hole through the tip of this very large fault, this plate boundary fault, and try to understand more about what happened here on the fault. This looks maybe a little bit strange because we're just at the very tip. And as a seismologist, we'd actually like to drill here, but this is just much too deep. Right now, no drilling operation can reach the fault at this one. And even this part was very difficult. So this is where we were able to drill, and maybe it's not representative of the whole fault, but it's certainly representative of the shallow portion here. And I said the shallow portion is important because it was the movement along this part of the fault that caused the ocean bottom to move, that caused the very large tsunami. So drilling into the fault here, we're trying to understand how did this fault move so much? What are the physical conditions on the fault here? How do we explain a fault that can move so far, that can move 50 meters, and then cause this very large tsunami? So this was the main purpose of this big project, this project that we call JFAST. And it uses this ship. And so with this ship, Chikyu, we were able to drill into the fault. Probably the oil industry, the drilling industry in Saudi Arabia has a lot of knowledge about drilling on land. But probably in Japan we have very good expertise on drilling in the ocean, especially for research. And we have one of the best tools for doing that. And that's this ship that we call DV Chikyu. DV stands for Drilling Vessel Chikyu. And so this was built about 7 or 8 years ago. It's run by an organization called IODP, it's run by JAMSTEC, which is the organization in Japan that operates the ship. It's pretty big. It's about 210 meters long. The height to the top of the derrick is 130 meters. It's over 56,000 tons. Usually there's about 150 to 200 people on board. It's got 6 different thrusters or 6 different motors on the bottom. That's important because when you're drilling, you have to keep the ship very, very stable. And so those 6 thrusters are actually sort of rotating motors that are always being controlled by the navigation to keep the ship very steady while the drilling is occurring. And one sort of very good advantage of this, it can drill in very deep water. And so we had to drill in very deep water to reach the fault, and so almost 7,000 meters of water, actually about 6,900. And then from the ocean floor, we drilled about 850 meters to actually reach the fault. So this is the tool, or this is the ship that we use to actually drill into the ocean floor to try to look at this big fault that moved during the earthquake. We call the project JFAST, that stands for Japan Trench Fast Drilling Project. As I mentioned, the main purpose is to understand the very large fault slip, maybe about 50 meters, that occurred on the shallow portion of the megathrust on the fault. And as I said before, we want to understand it because this is what caused the very large tsunami. Specifically, what we're trying to learn from the science, the kind of projects are, we want to measure the friction on the fault. We want to measure, what is controlling the stresses or the strength of the fault. We want to learn about the stress from the friction and also from sort of the regional stress patterns. And we want to look at the actual fault. What kind of rock is there? What kind of structure? No one has actually seen a fault before that's moved 50 meters. So actually just getting a piece of it and looking at it is very important and will tell us a lot about the fault. And so if we do all of this, we can hopefully understand what happened during this earthquake. And of course, if we understand what happened in this earthquake, we can begin to understand what might happen in future earthquakes like Nankai or Cascadia or other big subduction zones around the world that have the potential for making these very large tsunamis. So we have this very big project, and I'll talk a little bit more about it. Unfortunately, I can't give you a lot of results or a lot of answers today because we're still analyzing a lot of the data. We actually haven't collected all the data, and so it will still be maybe another year or two before we can really have some answers about this. But I'm going to explain some of the things that happened that are connected with this actual project. So here's a map again. So here's where the earthquake happened. The drill site was out near the eastern edge, and that's where the slip on the earthquake was very large. It's also where the ocean is very deep, and so this is where the ship went to drill the borehole. As I mentioned, the ship is run by an agency in Japan called JAMSTEC, but it's part of what we call IODP, and that stands for the Integrated Ocean Drilling Program. And so this is an international group of people that are doing a lot of drilling in the ocean. They drill to understand earthquakes, and they drill to understand many kinds of problems, probably even more projects than earthquakes. There's lots of investigations of climate change. By drilling into the ocean floor, they can sample the different sediments and understand what was the climate, what was the temperature of the oceans or the earth 1 million years ago or so. So anyways, this organization is always drilling holes into the ocean to learn about many different kinds of problems. And so understanding earthquake faults is just one of them. Okay, here's a picture of the actual site. And what this is again a cross section. So this is the ocean floor, and this is the water here. And all these black lines come from reflections of bouncing seismic waves. So it's actually a very large process where you have what we call an air gun. It sends little pulses down, and you record the reflections, and you can get an idea of what the structure looks like underneath the ocean floor. So here's the ocean floor, and this is what we think is the fault, or this is what we think is the boundary between the Pacific plate and the continental plate on top. So this is the actual plate boundary. This is where this ocean plate is going down or going to the west. And when you look at it this scale, what is this? I can't read it, but this is, I think 1 kilometer. You can see it's actually very complicated. And for our purposes, actually complicated is not so good. We actually want to go to a place where the fault is pretty simple and hopefully easier to understand. So that's why we didn't drill here. In this place, the fault seems to have lots of branches and lots of complicated structures, and there's also this sort of dropping down of the plate boundary here, which we think we can understand it or explain it, but we want to be here where the plate boundary or the fault looks much more simple, and hopefully all the slip happened on this portion here. Of course, it'd be nice to be way over here and very deep, but again, there's just limitations on where we could drill. And so this is the site. This is the borehole. From the bottom of the ocean floor, it's about 850 meters. And this is where we went to try to look. This is where we want to see this fault surface, to see what it looks like when it slipped during the earthquake. Okay, there was a big international team, so it was part of this IODP. So there were 28 scientists on board and about 120 crew, which was engineers and people running the ship and people operating the drilling. So scientists from many different countries, geologists, geophysicists, seismologists, geochemists, microbiologists all working on this project. And we had senior people and also students. So it was a very good mix of scientists that we had on board. There are many parts to this operation. The first part was what we call LWD, drilling, logging while drilling. And so this first part is we needed to just drill a pilot hole to find the fault. We had that picture where we thought we knew about where the fault is, but we wanted to know exactly where the fault was to make our measurements, to do the sampling. So the first thing we did was to drill a pilot hole, and there's all these geophysical instruments on the string. We measure resistivity, gamma, image. All these things just give us physical parameters of the rocks. And so if we can look at those different kinds of measurements, hopefully we can find exactly where the fault is. And here's the drill string, and this is the bit. So this is actually what's used to drill the hole, to drill the borehole through the rock. And so this is made of very hard metal, and all these little bumps are actually diamonds, because diamonds are one of the hardest material, and you need that to actually drill a hole through the rock. And so this is the what we call the bit. So this is what actually cuts through the rock as we're drilling the hole. And then above it are all these instruments. And here's some of the data that was collected, and this is probably hard to see, but the different colors or these different bumps show the different properties of the rock. And so in this pilot hole, we actually found two places, one at about 720 meters and one at about 820 meters where we thought the fault might be. And actually turned out this is where the fault was. It was at 120 meters. This was also a fault, but much smaller. And so this is where the main plate boundary fault was during the earthquake. As I said, the water was very deep, almost 7,000 meters, about 6,900 meters. And so we had a lot of trouble just during operations. Things didn't work correctly, or sometimes they broke. And most of this was just due to the very deep water. At 7,000 meters, the pressure is very, very high. And so a lot of the mechanical parts of the drilling and a lot of the techniques didn't work correctly the first time because no one's ever done this before. Chikyu, the ship, I think before this, the deepest water they had drilled in was maybe about 4,000 meters. So this was much, much deeper than anything that had been done before. And so there was a lot of, trouble. There was a lot of things that were learned that we didn't know before we tried. We had some bad weather at times, which also delayed things. Here's just one time when the weather wasn't so good. These waves are maybe about maybe 6 or 7 meters high. And so, of course, when the waves are this high, you can't drill because the ship is moving so much. And so when this happens, when it's really bad, people just take some seasickness pills and go to bed because there's nothing else to do. And so the waves were actually very high during some of the time that we were out there. This was in May, or April and May, which was not the best time, but not the worst time. And we lost maybe about 5 or 10 days to weather. And every time there was some trouble, or when the weather was bad and you had to bring up the pipe, it took a long time. And so just moving the end of the drill string to the bottom of the ocean and bringing it back up took 4 days, because it takes a long time to reach the bottom. And so you're on the ship, and what you do is you connect one of these pieces of pipe and you lower it down, and then you connect another piece and you lower it down. And these are 36 meters. And so to reach 7,000 meters, it takes maybe about 200 of these pipes. And so that's why it just takes so long to go down or to bring it up. In the opposite way, you bring up one pipe and you move it off and you bring up the next one. So it's a very long process because the water is so deep. And that was actually sort of rather frustrating, because every time something went wrong or you have to try again, it took 4 days to do this process. Okay, it was very deep, but that also meant it had never been done before. So we actually set some new records. For example, the greatest total depth below sea level. So a total depth of 7,740 meters from the sea level down to the bottom of the hole. This is the deepest research hole. Some of the oil companies might have gone a little deeper, but for research, this is the deepest hole that was ever drilled before sea level. First time the Japan Trench plate boundary was reached, and it's also the deepest fault core sample that was ever made. So it had never been done before, and so there are a lot of new technical milestones from this. One of the main purposes of it was to measure the temperature. And to measure the temperature, what we learn is how much friction. So how easily does a fault slip? If the friction is high, it means it doesn't slip very easily. There's sort of a lot of resistance. If the friction is low, it means it can sort of slide very easily. And the best way to measure the temperature, or the best way to measure the friction, is to measure how much temperature there is on the fault after the earthquake, because the more friction, the hotter is the fault. And actually it turned out during the main expedition in April, May, we were not able to put in the temperature monitors, but we got a second chance in July, and then we were successful. So what this photo is, this is the top of the hole, or what we call the wellhead. And so this is the bottom, this is the seafloor at 6903 meters, so very deep. The seafloor is actually very smooth down that deep. And so this is just a photo when we finally did get the temperature sensors put into place. Not too much living there, but every once in a while there's a strange looking fish like this that can swim by your camera. So this was put into the borehole on July 16th. And what it is actually there's a series of temperature sensors, just basically thermometers. And especially near the fault, we have lots of thermometers. And so what we hope is to measure something like this. What this is temperature as a function of depth. And right past the fault, we hope to see a little bump or a little temperature anomaly. So even maybe 1 or 2 years after the earthquake, we're hoping that there's maybe about 1 degree or maybe a few tenths of a degree of temperature change across the fault. And so that will really tell us the friction there. Right now we don't know anything because we haven't gone back to pick up the instruments yet. And we're going to do that in February, next month, soon. On February 10th, we go back to pull this string of instruments out of the hole and to actually look at this data. So we're all very anxious to see this. So this is one of the main results, or the main things that we hope to see from this experiment. The other thing we want to do is just get a piece of the fault, look at the fault, as I said before. And so there was lots of coring done. And what coring means is you actually go and bring up a piece of rock or a piece of mud that you get while the drilling happens. And so you analyze this, and there's lots of ways of analyzing it. Maybe you recognize this. This is for a CT scanner, just like that's used in the hospital. It's exactly the same thing, but instead of putting a human there, we put our core samples through the CT scanner. And we can get a very good picture and look at the core in 3 dimensions to see what's going on. So all of these samples that were taken are right now being analyzed very carefully to try to understand. And core number 17, JFAS 17, depth of 821 to 824 meters, is a very special core and is being looked at very carefully because this actually went through the plate boundary. This actually went through where the earthquake happened. Unfortunately, we didn't get the whole core. We only got maybe 40%. But even this is pretty good. Actually, it's very difficult to collect fault zone material. But from this even short amount of core, just this less than 1 meter, we're going to look at and see what does this plate boundary look at. What is the material that looks like that can make 50 meters of slip during an earthquake? One result we have right now is that the actual plate boundary, and by plate boundary we mean where the slip is happening between the Pacific plate and the continental plate, is actually very thin. It's less than 5 meters thick, where all this deformation is happening in repeated earthquakes. Earthquakes have been happening for thousands, tens of thousands of years here, but they've been happening on this very narrow zone. And so that's actually a very important result. And that's going to tell us a lot about this, the slip weakening or the slip concentration that's going on. And again, here's a close-up of this very important core 17 that we have. Another thing that's happening is people are doing experiments right now on this material. They're taking it into the lab and they're measuring how hard or how soft is this material. They're also taking this material and making little earthquakes in the lab to study the frictional properties of this rock. And so this is being analyzed very, very carefully because, like I said, no one's actually ever gotten a sample before of a plate boundary that's moved so much during an earthquake. So hopefully in maybe a few months or a year, we'll be getting many results from these kind of analysis of the core, analysis of the temperature, and hopefully we'll begin to really get some answers about why this very large slip happened on this portion of the fault. Okay, so in summary, there was very, very large slip on the shallow portion, and that caused a tsunami, and that's what we're trying to understand in this project. The project happened very fast. That's why we call it J-fast. So 13 months after the earthquake, we were able to go and collect the samples and put in the temperature sensors. Technically, it was very difficult. The very deep water and having no experience, there were lots of problems, but it also meant that we set some new records for drilling in the ocean. We were able to put the temperature sensors in July, and next month we'll go back and try to collect it and really try to understand these frictional properties of the fault. And all the analysis that's being done on the rocks right now, we're trying to look at the properties. One thing we learned already is there's actually a very, very narrow fault zone, a very, very narrow plate boundary for the subduction boundary there. So I think I'll finish up there. If you're interested in finding out more about this project, there's actually a very good web page that has a lot of information about the project and videos while we were drilling out there, and lots of information about our J-fast project here. And finally, I'd just like to thank all the people that invited me and worked on this project, and I appreciate all the help that I got from these people. So I think I'll stop there. Thank you very much.
Okay, thank you very much for this interesting and inspiring talk, Jim. So let's open the floor for questions, and if you have any, please come up to the stage and grab a microphone, otherwise we can't hear you. There's one question over there, and I'll leave that microphone and go to the stage.
Thank you very much for the interesting talk. But my question relates to the drilling. How long took it to drill that hole, approximately? How many days, how many weeks?
It actually really depends. If you are not coring, you can drill pretty fast. You can drill 800 meters in maybe 2 or 3 days. The thing that takes a long time is to take samples, because you drill about 10 meters and then you pull everything back up 7,000 meters. And then you drill another 10 meters and get your sample and pull it up. So when you want to sample, it takes a long time just because you're doing all these round trips. And since we didn't have much time, at the end we didn't core everything. We just said we want to core, from the surface to this depth, and then we skip some and we core a little bit more. And so the whole coring, I think, was about 2 weeks or so.
Okay, there's another question in the back there.
Yes, I noticed that you mentioned just briefly that you brought some microbiologists along, and I was curious, is that to study just as the life as the ocean goes down, or were they actually interested in looking at possible organisms in the core samples themselves, and if so, what did they find?
Right. Actually, I'm not an expert on this, but the microbiologists are always looking for signs of life. And it turns out at even these very deep places, there are microbes and things that are happening. And one thing that they're very interested in is When you get an earthquake or fault any place in the ocean, it releases a lot of hydrogen. And one idea is that this release of hydrogen activates a lot of microbiology activity. And they haven't found it yet, but they're looking at that right now and trying to associate these chemical changes with changes in the microbial activity. And so there's a few people that are looking very carefully at that right now. 800 meters is actually not so deep in terms of biology, so there's definitely organisms at that depth. Once you get to maybe 7 or 8 kilometers, it's much harder. But at this depth, there's definitely microbiology activity that's going on.
Hi. How do you determine where a fault line lies?
Exactly how deep it is?
Where, as in where it lies exactly, not necessarily how deep, but the coordinates of the fault line.
Right, so that was the purpose of the pilot hole and what I called the LWD. So we drilled one hole very fast, and it had all these geophysical instruments while it was drilling. And by measuring the changes in the rock properties, usually faults are sort of softer rock or might have more water. And so we can see these changes while we're drilling, and that's what we use to identify the fault. And actually, when you do that, you aren't sure, and when we did it, we actually thought there were 2 places that were possible. And so we targeted both of those, and then when we actually got the sample, we found out which of those 2 really was the real fault.
Yeah, just to follow up, what made you decide then it was the second, the deeper one? I mean, what were the different properties at these 2 places that you say, this is the one that ruptured in 2011?
So I'm not a geologist, but as soon as the core from the second one came out, the geologists got very excited right away. They took one look at it and they said,
That's it.
This is it. And the reason was it looked very much like faults on land. It had that very scaly fabric that they had seen on faults on land before.
Okay. I saw another hand coming up there.
Yeah. So my question is, like there is a large displacement in this earthquake. So you expect to, the friction to go down during the earthquake. I mean, you have a large displacement. So what kind of exactly frictional behavior you are expecting from this analysis of your data? That's first question. And the second question is, you showed the indentation depth of the tsunami. So have you tried some putting some realistic model and matching the indentation depth, like kinematic or dynamic models, these kind of steps?
Right, okay. The first question, if you're really interested, you should come to my lecture tomorrow morning. And I'm going to spend 2 hours talking about friction and different kinds of models. But very simply, in seismology, we have a lot of ideas, what we call slip weakening or friction reduction, which means that the friction is very high at the beginning, but once it begins to slip a lot, it suddenly drops to a different level, a dynamic level. And so there's lots of ideas, but not much data. And so that's one very important part of this project, is actually get a sample and try to get some data that we can use to understand a lot of these different kind of friction models or friction ideas that seismologists have been using. Second question about tsunamis. So a lot of work on tsunamis, and one thing that is done quite a bit is to do almost the opposite of what you said. And what that means is you put in the tsunami data and you do an inversion, and that can tell you how much the fault slipped or how much the ocean floor moved during an earthquake. So the actual modeling of tsunami data is actually, it's understand fairly well. So we can do both forward models to put in a model and see how that matches the tsunamis all along 500 kilometers of the coast, or we can do the opposite. We can do the inversion. We can just use the data that was collected and back out how much the ocean bottom slipped during the earthquake.
Okay, there's another question in the back here.
So could you explain, please, a relationship between Earthquake and Tsunami, you said there was strong earthquake and many other earthquakes. How about tsunami? Was only one big wall going, or were more smaller walls?
Okay, that's a good question. The aftershocks were all much, much smaller than the main shock. Well, there was a 7.5, which is pretty big, but compared to 9, it was still pretty small. So the aftershocks would have also caused tsunamis, but very tiny. So basically, maybe you saw a few centimeters from those. So the big tsunami was only from the main shock. But I showed that video, there's several waves. And so those different waves mean that it was actually a very complicated process. Probably different parts of the fault moved different amounts. And also different deformations at different depths would have caused different waves. So the tsunami or the multiple tsunamis came from the main shock, but they arrived over a period of about, I think about 30 to 40 minutes. And people said actually the first one wasn't the biggest. The biggest was the second or third. And the reason for that is the biggest was coming from very far away. The biggest was coming from where we were drilling, where there was very large slip, but it's very far from the shore, so it took a long time to come. And that's why the later part of the tsunami was bigger than the first part.
Okay, there's another question way in the back.
Thank you for the talk. So my question is just a little technicality. You said that the temperature measurement is quite crucial for the work. And you also mentioned that you only expect maybe like a couple of degrees of changes in the end at that zone. So when you drill, obviously the seawater goes in, and doesn't it affect the measurement in the end? And you're there for like a couple of months. So it seems like that the error can be very large, and you only expect a couple of degree of changes. So how does that work?
Yeah, that's a good point. When the earthquake happens, there was probably a very large temperature change, maybe 100 degrees or more. But we were there about 1 year later, and so we expect it to be 1 or 2 degrees. And you're exactly right. While you're drilling, it disturbs it. So we measured the temperature while we were drilling, but that's not very useful. So that's why we put the temperature sensors in and left them there for about 6 months. And during that 6 months, the temperature should equilibrate. And so the rule of thumb is you take the drilling time and multiply by about 2 or 3, and that's how long it takes for the temperature to go back to the ambient level. So that's why 6 months, it should have all settled back to the disturbances from the drilling should go away, and we should be able to see probably much less than 1/10 of a degree, maybe even a few hundredths of a degree at that time.
So the seawater is inside still, or no?
So of course there's water in the hole, but if you just leave everything and you let it sit there for a few months, all the temperature equilibrates. And so the water equilibrates with the rock wall. And the big problem is if there's flow up and down, and that could cause a big error. And so that's something that we don't want. And so you want everything to be sort of very calm and have the water not move and sit there very stably for about 6 months, and then we should be able to get a good measurement. And so those temperatures are recording continuously. They're taking one measurement every 10 minutes for 6 months.
Okay, Olaf, you have another question?
I just want to follow up on this question. How you define the temporal diffusion coefficient then? Because you have to get an understanding of how your temperature decreases in the hole from 2 years ago to now.
I'm sorry.
I guess it doesn't isn't it, I guess it's not enough if you just measure the temperature, but you also measure the temperature, but you also have to know how temperature decreases over time, right? How it diffuses out, and is that constrained beforehand, or are you doing the time series?
So the idea is that when the earthquake happens, the temperature goes up like a step function. So it's just like if you move your hand, it gets hot. And so the temperature goes up, and then over a year, it just gradually, the heat diffuses, and so the temperature gradually goes down. And so if you know the diffusivity and you know the time, then you should be able to calculate how much heat or how much the temperature was or the heat was generated at the time of the earthquake. Does that answer your question, maybe? Which number? The diffusivity. Okay, that's a good question. And we get that from the core. So we have a sample of the rock, and we take that back to the lab, and you essentially just heat it up, and you see what's the time constant of that piece of material. And so that's the easy part. The hard part is usually there's water in there. And the water may be flowing or not flowing, and so accounting for any kind of fluid is actually much harder than, it would be much easier if it was just the rock, but it's sort of that interaction between the water and the rock that can cause some problems.
Okay, any more questions from the audience? If not, then let's thank Jim Mori again for this very interesting talk.
Thank you.
And I have a little gift for you here. It's the web Keynote speaker gift. Let's see if I can open this. There it is. All right. So this was actually turned around. It should be this way. All right. So here's your Web 2013 gift and medal for you. And thanks again for this very inspiring talk. And I hope we have interesting discussions the next few days. All right, thanks everyone for coming. And as Jim Mori was saying, he is teaching 2 courses in the next 2 days. If you haven't signed up yet, do so, or maybe just show up and sneak in and learn more about these events and earthquakes in general. And